Hello, everyone. Welcome back to today's session of Discrete Maths 2. After a first session of preaching that I hope was not overly boring, what we are going to do now is start dancing. We're going to start our journey through the topics covered in this course. I've decided to start the course with a topic that ties in nicely with what you're going to do in the data structures course. And that also has to do with one of the important aspects of the genetic heritage of any honest-to-God computer scientist, namely recursion. The R word. Have you seen recursion before? Okay, some of you have, some of you haven't, but it really doesn't matter because we are going to cover the basics of recursion from the beginning. Now, the reason why people like me today introduce the concept of recursion to you guys and gals is because computer scientists think recursively. What does that mean? I mean, if you take the DNA of any computer scientist, you will find the R gene in it somewhere. For R stands for recursion, the recursive gene. No matter what programming language you use, you will define data types in this programming language. Some of these data types will be given to you, others you can define. Recursion plays a fundamental role in defining data types. Now you may say, I mean, why? Well, the reason is that by defining data types recursively, what you're doing is to define a recipe, a procedure for constructing objects of the data type. This data type could be lists, trees, stacks, queues, all kinds of lovely things that you will meet in the data structures course. And whenever you want to describe a collection of objects, we computer scientists are not just happy to say, well, this collection of objects is a set of things that look like that. We want to have ways of constructing these objects. Not only we want to have ways of constructing these objects, then we want to define programs, functions, methods, procedures, call them whatever you like, that actually operate on objects of that type. And if the objects of that type are defined recursively, there is a beautiful way, which is at the heart of a discipline of programming called functional programming, which is increasingly popular and will become increasingly popular in the multi-core age that we are living in. Once you've defined objects recursively, you can define operations on these objects recursively by following the way in which you've constructed them. Moreover, once you've defined your functions, you want to be able to convince yourself that these functions actually do what they're supposed to be doing. If they're supposed to sort object of an item, well, they better sort. If they delete all of them, well, it might be good as a delete operation, but not as a sorting operation. Of course, you never make mistakes when you write programs, unlike me and most other human beings. But once you actually write any program of some kind, you want to ask yourself, does this program actually do what I wanted it to do? Well, some people, like me, like to prove these properties. And if you've defined your function recursively, then there is a beautiful way, a very efficient way of proving that what you did actually works, which is an inductive proof. I'm pretty sure that induction is not something that is completely new to you. You heard this before, haven't you? If you've never heard of it, scream now. I like the sound of silence, like Simon and Garfunkel here. Fantastic. So now I'm sure you're going to ask me, okay, this is all mumbo jumbo. Give us examples. What does it mean to define a data type recursively? And how can we go from the recursive definition of the data type to functions operating over objects of the data type? And once I've done that, how can I actually prove properties of what I just defined? So let's do it. Let me give you an introduction to the mother of all data types, at least in functional programming. That's the data type of lists. How do we define a list? Well, remember, I'm wearing my recursive contact lenses on. So I want to use recursion to define objects of type list. Now, when you have the definition of a set like the set of the natural numbers, how do you define it? The set of natural numbers contains 0, which is the base case of the definition. It gives you something, a natural number, that you can use to actually construct new ones. And then it tells you how to construct new natural numbers from ones that you've already built. If n is a natural number, then n plus 1 is a natural number. Any natural number can be constructed by starting from 0 and then adding 1 to it sufficiently many times. So if you want to define the natural number 35, you start from 0 and then you do plus 1, plus 1, plus 1, blah, 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 35 times. Nothing else is a natural number. The only things which are natural numbers are the numbers that you can construct using the recipe that Jamie Oliver just gave you. Why don't we do the same with lists? And that's exactly what is written there on the slide. For the natural numbers, we start from 0. With lists, we start from the simplest possible list, namely the empty one, the list that contains no element. This gives us something to work with. That's the base case of the construction, which is the one that you have over here. Now, if we only had the empty list, you would agree with me the data type would be pretty boring, wouldn't it? There isn't that much that we could store just using the empty list. We could store nothing. So let's assume that we are, for simplicity, trying to define lists of binary digits. These are lists whose elements are bits. The second step of the construction tells you how to build longer lists from lists that you've already built. So how do you do it? If Father Christmas brought you under the Christmas tree a few days ago a list L, how can you use that list L to construct a longer list? Well, since these are supposed to be lists of bits, I told you I'm trying to define lists of bits. So what is it that you can do? You can take a bit, a 0 and a 1, or a 1, and stick it at the front of the list L. That's exactly what this says. If somebody gives you a list L, then the list that starts with 0 and then continues like L is a binary list, a longer one. Otherwise, you can stick a 1 in front of L and get another binary list, which is longer than the one that you started from. Finally, nothing else is actually a binary list. And this is what this adjective here, smallest, actually means. This basically says that the only binary lists, the only good, honest-to-God binary lists, are those that you can construct starting from the empty list using the rules at step 2. Some number of times, some finite number of times. So far, so good? Have you seen something like this in the problem-solving course? Perhaps. Perhaps not. It doesn't matter. You don't need to have seen it before. So, for instance, thank you. I was falling asleep, so somebody woke me up now. Thank you. Okay? So, how do we use this definition? Well, suppose somebody asks you, Well, let's use this fantastic tool here. Okay, suppose somebody asks you, okay, is this thing here 0, 1, empty list, a list? Is this something which is in bin list? What would your answer be? One of your colleagues, or perhaps more than one, said yes. And the answer is right. Why is that? Well, elements of this data type bin list are exactly those things that I can construct using the rules that I gave you on the slide. That is to say, you should be able to build this list if it is to be a good, honest-to-God element of the data type binary list by starting from the empty list and then adding bits on top of it. And this is possible. Why? Because by rule 1 that I gave you before, I know that this thing is actually an element of bin list, the data type of binary lists. So far, so good. Now, the second rule says, since you now have the empty list in your data type, you can stick a bit in front of it. So by rule 2, I know that 1 followed by the empty list is also in bin list. This is the list that only contains the bit 1. Question? The question is, what do the 2 dots actually mean? Well, that's the constructor that we use to build lists. Now, the notation comes from the functional programming language ML, which I will show you an example of on the following slide. But that's a good question. That's the constructor that we use to add bits in front of lists to generate new lists. It's basically an operation that takes 2 things. It takes a bit as first argument and a list as second argument, and returns a list of bits. Fantastic. Excellent question. Well, now the second rule again tells me that since this thing here is a list, and let me remove this bit that I don't need here. Since this is a list, I can stick a bit in front of it and obtain a longer list. Well, since my goal was to achieve this element here of the data type, then the bit that I stick in front of the list I have in my hands is a 0. So I use rule 2 again to construct, to prove that this list here is a binary list. So, happiness. This thing is a binary list because we've actually been able to construct it using the rules that Jamie Oliver gave us in the recipe for binary lists. Okay? It's not mind-boggling. The important thing is that binary lists are exactly the things that I can construct using these 2 formation rules that I have here. The first rule tells you, okay, these are the smallest binary lists. Well, there's only one, it's the empty one. The second rule tells you how to build complex lists, longer lists from ones that you've already built. Let me ask you a question. Suppose that I had actually inadvertently forgotten to put rule 1. All I had was rule 2 that says, if somebody gives you a list, then you can build a longer one. How many lists would you be able to construct using only rule 2? 0, none of them. Why? Because rule 2 says, if you've already built some list, then you can make it longer. But if you don't have any list to start with, you cannot use rule 2 for anything. So you're not able to construct anything. This is like somebody gives you an empty box of Lego bricks and say, build. This is the rule. If you have a Lego brick, then you can stick it in front of another Lego brick and build a bigger building. Yeah, but you didn't give me any bricks. So what can I build using this rule? Nothing. Absolutely. Wonderful. That's why when you define something recursively, it is always a good idea to have a base case. Otherwise, you're in trouble. Do you agree? Okay, so whenever you define something recursively, at least one base case, this tells you how you can start building stuff, and then perhaps one or more collection of rules that tell you how to build bigger things from things that you already built. It's like Lego building. Absolutely. Nothing more, nothing less. Okay, so let me ask you to do something for me. I told you that we were going to play table tennis, and you're actually going to do exercises during the lecture. Suppose that I don't just want to define lists of binary digits, but I want to define lists of elements of some type A, which could be characters, integers, whatever. So I want to define a data type lists of A, which are lists of elements of type A. How would you define them? How would you define list A? And let me put up the drawing tool here. And let me get a fresh page. Why not? This is not real paper, so we can be wasteful. Okay, so I want to define a list of A. And I want to define it recursively. So how do I go about doing that? We start, as your colleague is saying, from a base case. Now, what is the base case? What is the shortest list of elements of type A? The empty list. This was not a trick question, was it? So rule 1 says the empty list is an element of the set list of type A. Question. The question is the base case always an empty list? Well, it depends on what you're trying to define. If you're trying to define the collection of non-empty lists of type A, then the base case would be lists of length 1. So it depends. The answer is it depends on what you want to do. But I didn't say non-empty lists. I said any lists. So in that case, the empty list is the base case. Okay, now I have at least one list to work with. Now I want a rule that I can use to build longer lists from lists that somebody have given you. Oh, by the way, sort of another thing that you miss by watching the YouTube recordings is that you miss a little bit of Italian hand waving, but that's it's not a big miss anyway. Okay? So suppose somebody gives you a list L. So if L is already something of type A that you've already built, where this means belongs, then how do you make it longer? Okay, yes, you add something at the beginning, like we were doing before. You add something at the beginning of the list L that you already have. Now, what is it that you're allowed to append? Some element of the set A. So if A is the set of integers, you append it, you start the new list by a new integer. If A is a set of characters, you add a new character. If A is if A is the set of your former girlfriends, you add the name of your former girlfriend or boyfriend, whatever. In general, so if L is a list of type A that you've already built, and A, small a, is an element of the data type, capital A, then you can build a new list which starts with A and then proceeds like L, and this will be a list of elements of type A. And in particular, list A is the smallest set satisfying these two conditions. Now, what does smallest here mean? It means that an element of type list of A is there if and only if you can construct it using these two rules. So something is an element of type list of A if and only if you can build it using these two rules. Exactly like an element of bin list is a list of binary digits if and only if you could build it using the rules that I gave you before. So for instance, 3 empty list is not an element of bin list because there was no rule that told me you can take a binary list and add a 3 in front of it, because 3 is not a bit. Question? The question is, how would you add more than one element into the list? By recursively applying rule 2. Rule 2 says, give me a list. No matter what that is that you've already built, you can always add something on top of it. So you start from the empty list, you add one element to it using rule 2. You want to add more, use rule 2 again. You want to add more, use rule 2 again. You want to add 1 billion elements, you use rule 2 1 billion times. It takes a long time, but you can do it. And you don't have to do it. You let the computer build lists of length 1 billion. You don't do it by hand. Okay, what would the first rule look like? That's the question. If we assume that we are defining the list of the collection of non-empty lists of elements of type A. Excellent questions. So, only one. So in that case, the base case would look like this. In fact, there would be more than one base case, because now there are many different, possibly many different lists of length 1. These are the smallest lists that you can have. So if you want to define non-empty lists, then you would use a new base case, let me call it 1 prime, which will look something like this. If A is an element of the data type capital A, then you can write it however you like. Or if you prefer, you could write it this way. But what really matters is that now the base case is lists of length 1. And there could be several of those, depending on what element of A you put into the list of length 1. So if it's lists of integers, then it would be the list of length 1 that contains 0, the list of length 1 that contains 1, and so on. These are all base cases now. Note that even if this rule that I've written looks like an if then else, the condition here does not talk about lists of. So it's not recursive. It just says, okay, you're defining lists over the data type A. Give me an element of the data type A. I will give you a list of length 1 that contains only that element. So there is no recursion, unlike in rule 2. Rule 2 is recursive because it's defining lists in terms of lists. That's what recursion is all about. Self-referentiality. What I just said is false, or what I just said is true. I'm uttering a sentence which talks about the sentence that I just uttered. This is typically very dangerous, but computer scientists have learned how to tame recursion. In fact, recursion is really at the basis of everything that we do. For instance, you use a compiler for your favorite programming language, I guess. So that's a compiler, say, for C++. Is that what you've learned? I guess so. Now, can you write a compiler for C++ in C++? Have you ever thought about it? If you haven't, sure you can. So you can write a compiler in C++ for C++. But this compiler can compile any C++ program, including itself. What's that? Recursion. An interpreter. Have you ever seen interpreted programming languages, like Python, for instance? You just type your command, poof, out comes the answer. That's what an interpreter is all about. It simulates any program that you can write. Well, you can write an interpreter for Python or for any programming language in that programming language. So this means the interpreter can execute itself. Recursion. Without recursion, you will not be able to do any of those things. So you see, recursion is your friend, is our friend, is not an enemy, even though it takes a little bit of time to understand it. And that's why we are here. So far, so good. Any questions about what we've done so far? Because actually now the fun starts. Well, not that what we've done so far was not fun, but it was not nearly as much fun as what we're going to do next. So I told you before that once you define some object, some data type recursively, then you can actually define beautiful operations over objects of the data type by using the power of recursion. So you define recursive functions over recursively defined objects. And that's really the bread and butter of functional programming. Let me go back to the question I got before. Why this strange symbol to denote, to write lists, adding stuff at element in lists? Well, that's how you write things in many functional programming languages. So what you see here is a function is a good piece of code in a programming language called ML, one of the core functional programming languages together with Haskell that I hope you will learn at some point. Certainly, you will meet it in your programming languages course, but perhaps there will also be courses on functional programming. This is actually a piece of ML code. Note, you're defining a recursive function length by following the recursive definition of lists. Remember, our lists defined. You say, what is the smallest list, which is the empty list. And then you said how to construct a longer list from a list that you've already built. How did we build it? By adding something, an element, on top of it, in front of it. Well, you can define a recursive function of a list by following exactly the definition of lists. You want to define how a function, say length, operates over any list? Well, all you need to say is what it does on the empty list, which is the base case, and what it does on a composite list, assuming that you already know how it works on the shorter sublist. So this is what this function actually does. The length of the empty list is, of course, 0. What is the length of a list that starts with x and then proceeds like the list rest of x? It's 1 plus the length of the rest of the list. 2 lines of code. No while loops, no for loops, no iteration. You just unleash the power of recursion. And it's absolutely clear that this thing works, isn't it? In fact, ML can be interpreted. So if you ask the ML interpreter, what is the value of length? The ML interpreter will tell you, well, length is a function that takes as input lists of type A, that's what it means, and returns an integer. Note, this is a polymorphic function. What does this mean? It means it works whether the lists are of integers, bits, characters, it doesn't matter. You don't have to define a separate length function for lists of bits, for list of integers, for list of grandfathers. It doesn't really matter, because all of these functions operate in the same way. They just count how many elements there are. It doesn't really matter what the type of the element is. So you can actually use this function for all the different types of lists that you can ever imagine, even lists of lists. Now, how do we write this type of function? Well, we make it even more programming independent. And this is how we are going to write functions like this. What matters is the structure of the definition. This is pseudocode, but it looks a lot like real code in a functional programming language. You want to define a length function over lists of bits, or over lists in general. How is it that you define it? You define what it does on the base cases, the empty list. In this case, the length is 0. And then you define what it does on the recursively defined objects. What are the recursively defined objects? They are lists. They have at least one element, the head of the list, and then there is a list L that follows them. So what is the length of a list that starts with X and then continues with the list L? It's 1, namely the X, plus the length of the list L. Okay, so for instance, if somebody asks you what is the length of the list 1, 0, you would say, how many elements are in there? 2. It takes 2, baby, to make the list 1, 0. And how do we compute this? Simply by applying this definition recursively. Question?
Is there any reason why there are parentheses around brackets in the base case and lower, for example, not in the upper, or is there anything that matters?
Is there any reason why, the question is there any reason why there are parentheses here? You mean the square brackets?
Yeah, not in the base case or
Okay, so here I just took a piece of ML code where it's not necessary to put the parentheses around the length. Here I'm just sort of being very pedantic, and just in order not to confuse you, I'm just giving you sort of the definition of a function. Okay, so I put the parentheses because that's how you define a function typically in mathematics, or in a programming language, you would call the name of the function with the parameters. And typically you would put brackets around, but it doesn't really matter, provided you use your notation fairly consistently. Now, what I would like you to do is to actually define some function for me. I'm pretty sure you could actually use this definition to calculate the length of this list. You can do that at home. But let's do some exercise. I want you to define a recursive function that takes 2 arguments. The first argument is a bit, 0 or 1. The second one is a binary list. And it returns a natural number which counts the number of occurrences of the bit B, the first argument, in the list L, which is the second argument. Do we understand what we want to do? I want to define a recursive function, count, such that if you call count BL, where B is a bit and L is a list of bits, the result will be the number of occurrences of the bit B in the list L. So, for instance, if B is 0 and L is 0, 0, then the result will be 2. If B is 0 and L is 1, 0, the result will be 1. If B is 0 and L does not contain any zeros, the result will be 0. Okay, shall we try? Practice makes perfect, so let's do it. Okay, so I asked for a recursive definition of count BL. So let me write the specification once again. Count BL should be equal to, should return the number of occurrences of B in L. B is a bit, L is a list of bits. Hello, is there any sign of life out there? Fantastic. I asked for a recursive definition, so there is only one thing we can do recursion on, namely the list. So what is the base case? What is the smallest list? The empty list. So we start by saying what count does when the list, the second argument, is empty. In that case, what the result is, what is the result? 0. There's nothing in the empty list. Well, so far so good. You're halfway through. Why? Because now all you need to say is what happens when the list L is not empty. So the second case is if the list is non-empty, it will start with some bit B prime, and it will be followed by the rest of the list. You know, pattern matching is a very useful computational paradigm, especially if you're doing functional programming. Okay, so if a list is not empty, it must pattern match with the pattern bit followed by a list. Okay, so what do we do now? Now we need to consider some cases. Okay, what are the cases that we need to consider? Think aloud. Okay, so you have a bit B, and you have a list that starts B prime followed by L. And you want to count the number of times that B occurs in the list B prime followed by L. Okay, so what are the possibilities? Absolutely, if B and B prime are equal or not. So you can write an if then else. Very often I just put it like this. So if B is equal to B prime, what is the answer? So if B is equal to B prime, you found one occurrence of B in the list, the first one. So we just remember that we found one. It would be 1 plus what? Count BL. That's a recursive call. Okay, let me sort of read this aloud. I'm counting the number of occurrences of B in the list B prime L. Since B is actually equal to B prime, I found one occurrence. So it's 1 plus what? Well, the number of occurrences of B in the list L. And how do I find them? I unleash recursion. I just recursively call count B on the rest of the list. And recursion will do the computation for me. I don't need to count explicitly. I just let recursion do it for me. Now, if you're like me, this is cool. And I think it will be cool for you. It's just so nice. Okay, but that's only half of the work. Because there is another case. What if B is not B prime? That's the only other possibility. Either B is equal to B prime or it isn't. If it isn't, how do I count the number of occurrences of B in B prime L? Well, there's none at the beginning. So where are all the other possible occurrences? In L, in the rest of the list. And how do I find how many they are? Count BL, I just call recursively count. Fantastic, I unleash recursion. Bingo, we define the function count. And of course, instead of the curly braces, you can put an if then else if you like. But you see, yes, question.
So we start from the list, yes. Then we check if the first element is 1 or 0. And then we call the same function with the list, which is 1 element short. Yes.
Absolutely, absolutely. So what your colleague is saying is more of than a question, is a statement.
How it is written, because we have that B prime is added to L, yes?
Yes.
And it's quite strange because it would say us be adding something.
Okay, so the question is, the way I've written the function looks a bit strange because it looks like I'm adding something. Now, you see, the definition of this function completely patterns the definition of the data type on which it is supposed to operate, namely binary lists. And that's exactly the point. You define binary lists recursively by using two rules. The first one says the empty list is a binary list. The second one says if you have a binary list L, you can stick something in front of it and obtain a longer list. This tells you the two possible forms that binary lists can have. They are either empty or they look like this. They have a first element and then the rest of the list. So here I'm not adding anything. I'm just stating the pattern that the list should satisfy in order for the second clause of the definition to apply.
I think about it as deleting an element and then calling the function of the list of the right way.
Okay, the question is, should I think of it as deleting an element and then calling the function? So it depends on the actual programming language in which you eventually implement this. So what I'm using is what we call a pseudocode. It's a pseudo programming notation that looks very much like a functional programming notation. What matters for me is not the precise form in which you write these definitions. And I'm pretty sure that many of you have written similar definitions in the problem-solving course. What matters for me is how you think recursively in defining these functions. Now, in a functional programming language, that's what you would write because pattern matching is built in there. If you want to implement a functional type of notation in C++, then perhaps you need to work a little bit more. But that's the way in which you proceed. Question? Yes. Okay, the question is, what do you do with the 1 plus here? Okay, well, remember, I'm trying to define a function of the following type. You know, types are important, so we need to understand what is the input type of the arguments and what is the output type, despite what JavaScript may tell us. Okay, so count is of type bit types bin list, and it returns a natural number. Okay, so this thing here should better return a natural number. Okay, so you have a 1 plus here. So 1 is a natural number. Plus is a good, honest-to-God operation of the natural numbers. What number is going to be returned in this case? By recursion, count BL will return a natural number. The number of elements, of occurrences of B in the list L. Once recursion returns that number, you add 1 to it and return the result. So the important thing is that count BL is going to return a number. Once that comes, the overall result of the computation will be 1 plus the result that count BL returns. That's what you do with it. Perhaps the best way to understand it and to finish today's course section is actually to calculate count BL on an example. Even though it's boring, let's do it. Because sometimes by doing boring stuff, one actually understands something, believe it or not. So I'm doing this for myself. So suppose I want to figure out what is the result of doing a short computation. So you will excuse me for that. I'll do count applied to, the list that only contains 0. Okay, how do I compute it? Well, do I use the base case? No, because my argument list is not empty. So I should use the second clause here. Now I pattern match. This is my B. This is my B prime. This is my L. This is called pattern matching. Computer can do it, so can we. Because we are computers, after all, of a certain type. So in this case, I mean the first condition, because B is actually 0 and B prime is also 0. So what is the result? The result is going to be 1 plus count the number of zeros in the empty list. Now, that's not something I can compute yet. I need to figure out what is the result of calling count 0 on the empty list. But now it's easy. Why? Because now I can use this clause, the base case, that tells me that no matter what B is, the first argument, in this case it's 0, if we are looking at the number of occurrences of a bit in the empty list, the result is going to be 0. So count of 0 in the empty list is going to return 0. So what I'm evaluating is 1 plus 0. And now I can use my knowledge of arithmetic to figure out that the result is 1. And since it looks like physics is on its way, unless there are any questions, we can call this a day. I'm even poetic today. It rhymes. And since everybody's evacuating, I assume there are no questions. Okay, see you on Thursday, where we will continue doing exactly this kind of stuff. Oh, well, there should be 255 students in this course. So, yeah. So this is fewer than...
Yeah.